You are holding a single sheet of paper, handwriting on one side. Yours. Now put yourself somewhere you will never be. At the boundary of a black hole, close enough to see the light bending around it, and you let the page go. It falls. It crosses the edge. And then you wait. You wait longer than this universe has existed until the black hole itself has thinned away to nothing, and the region of space where it sat is empty. One question. Where is the page? There are only two possible answers, and each one destroys something we were certain of. Either the universe is capable of erasing permanently and completely, or everything you dropped came back out, and nobody alive can tell you how. For most of the last century, that question had no urgency, because a black hole was forever. Then we learned that it is not. Start with the two descriptions of nature that collide here. Both of them have been tested to extraordinary precision. For decades, they never had to be in the same room. The first comes from general relativity. A black hole, once it has settled, is almost featureless. You can describe the entire object with three numbers: how much mass it has, how fast it spins, what electric charge it carries. Everything else is gone from the outside description: a star, a planet, a library, a person. Drop any of them in and the black hole tells you nothing except that it got heavier. The second comes from quantum mechanics, and it is stricter than most people realize. Nothing is ever erased. Things get scrambled, spread out, made unrecoverable in practice. But the rule underneath insists that the present state of the world always contains enough to reconstruct its past. Burn a book, and the writing is not destroyed. It is in the smoke, in the ash, in the light that came off the flame, hopelessly scattered and still there. Those two statements only have to be reconciled if a black hole can end. And then Stephen Hawking showed that it does. His result was that a black hole is not perfectly black. Quantum effects at the boundary force it to glow, extremely faintly, giving off a steady emission that we now call Hawking radiation. If it emits, it loses energy. If it loses energy, it loses mass. And if it loses mass, it is not permanent. It shrinks. Eventually, it is gone. And the emission depends only on those same three numbers: mass, spin, charge. Nothing about what fell in. How faint is faint? A black hole with the mass of our sun would sit at roughly 60 billionths of a degree above absolute zero. To finish evaporating, it would need something like 10 to the 67th years. Write a 1, then put 67 zeros after it. This universe is not yet 14 billion years old, and there is a detail that should unsettle you more than the number does. The sky itself, the faint heat left over from the beginning of everything, is warmer than any black hole we know of. Which means every black hole out there is currently absorbing more than it gives off. Not one of them has begun to die. This is an argument about an event that has not started anywhere we can see. It did not become a crisis when it was calculated. It became a crisis when the man who calculated it stood up in a room full of his colleagues and said he had been wrong. Before any of that, a young researcher named Jacob Bekenstein noticed something that should not have been true. He argued that a black hole has to have a measure of how many different ways its insides could be arranged, the same measure we assign to a gas or a hot iron bar. And when he worked out how large that number could be, it did not depend on the volume of the black hole. It depended on the area of its boundary. That boundary has a name: the event horizon, the surface past which nothing returns. And Bekenstein was saying that the capacity of the entire object is set by the size of that surface, not by the space enclosed inside it. That is a very strange thing for a physical object to do. Everything else in nature holds what it holds according to how much room it has. Hawking objected. Then his own calculation of the glow proved Bekenstein right in outline and handed the field a paradox instead of a resolution, which is how three physicists came to sign a wager. Hawking and Kip Thorne on one side, holding that the information really is destroyed. John Preskill on the other, holding that it survives. The loser would buy the winner an encyclopedia, and the joke was buried in the stake. An encyclopedia is an object you can pull information back out of at will. Years later, at a conference in Ireland, Hawking asked for time on the schedule. He told the room he had changed his mind. He now believed that information escapes, and he handed Preskill a baseball encyclopedia in front of an audience of physicists. He joked afterwards that given how useless the information coming out of a black hole would be, he should probably have handed over the ashes instead. That should have been the end of it. It was not. Thorne refused to concede, and has still not conceded. Preskill took the book and then said publicly that he was not certain he agreed with the reasoning behind it. The most famous surrender in modern physics settled almost nothing, because nobody in that room could show step by step how the information got out. What changed was a conviction, not a proof. So here is where we are. A black hole that glows, radiation with nothing written on it, and an ending that has to be accounted for. This is where it stops being a puzzle and starts being something people take home with them. Look closely at how the glow actually happens, because the version most people have heard leaves out the part that matters. Empty space is not empty. At the smallest scales, it is restless, full of pairs of particles that appear and cancel each other out again so quickly that nothing is left behind. That happens everywhere, including right next to a black hole. But at the boundary, the geometry is severe enough to interfere with the canceling. One half of a pair falls in, the other half gets away. The half that gets away carries energy off, and the black hole pays for it by shrinking. Now, the part that matters. The half that escapes is not independent. It is linked to the half that was trapped, in the particular way that quantum objects born together stay linked. And on its own, separated from its partner, the escaping half carries no pattern at all. It is heat and nothing else. Measure it and you learn the mass, the spin, the charge. You learn nothing more, because nothing more is written on it. That is the whole problem in one sentence. The trouble with Hawking radiation is not that it is faint, it is that it is blank. So run it forward. The black hole shrinks, and the glow gets stronger as it does, and near the very end, it goes quickly. Then there's nothing there. What is left behind is a cloud of featureless heat that could have come from anything at all. Two black holes, one that swallowed a national library and one that swallowed the same weight of iron, would radiate identically and end as identical clouds. The past is no longer reconstructible from the present. Not difficult, not impractical, impossible. There are three serious ways out of that, and every one of them costs something. The first is to accept it. Information really is destroyed, and quantum mechanics has to be amended to allow it. This was Hawking's original position, and the price is severe. If the rule can fail at a black hole, then it is not a rule. It is an assumption we have never had reason to question. The second is that the radiation is not blank after all. The information is written into the relationships between the escaping pieces, spread across the whole emission, rather than carried by any part of it. Too subtle for the original calculation to detect. That calculation treated the black hole as a fixed background and ignored how it responds to its own glow. The price is that something has to carry a record across a boundary nothing is supposed to cross. The third is that something is left behind. Evaporation stops just short of the end, and a tiny residue holds what fell in permanently. The price is an object smaller than a single particle that has to contain an unlimited number of internal arrangements, which creates fresh problems of its own. And then there is a fourth possibility, which is less a solution than a trap. Work carefully through what can be linked to what. A quantum object can be fully linked to one partner, and that is the limit. If the late radiation has to be linked to the early radiation in order to carry the information out, then it cannot also stay linked to the partner it left behind. And if you break that second link, the energy sitting at the boundary is no longer gentle. It is enormous. Not a smooth surface you drift across without noticing, but a sheet of lethal energy sitting exactly where the boundary is. An astronaut crossing it would not feel nothing. They would be destroyed on contact. That contradicts the founding assumption of general relativity, which is that falling freely should feel like nothing at all. So the field split again, this time over whether saving the information costs us the horizon. Step back and see what is actually being wagered here. If information is destroyed, then the principle that the present contains its past is not a principle. And it does not fail only near black holes. It fails everywhere, for everything, because a law with exceptions in the strongest gravity we know of is not a law. It is a local approximation. If information survives, the consequence is stranger. The inside of a black hole is not a sealed room. Whatever is in there is somehow already accounted for out here, in radiation that has been leaking for an unthinkable length of time. And if what is inside is already outside, then the separation between the two is not fundamental. Distance itself becomes something that emerges from a deeper description. Which brings us to the argument that finally moved the field. It began with a question about timing. Don Page asked what the escaping radiation should look like over the entire life of a black hole, if the rules of quantum mechanics hold. Not at the end. Throughout. His answer was precise. The link between what has escaped and what remains inside has to build for a long while, reach a maximum when the black hole is roughly half gone, and then fall away, all the way back to nothing, as the last of it radiates. It has to fall, because at the end there is nothing left inside to be linked to. That trajectory has a name. It is called the Page curve, and it is what the survival of information demands. Hawking's calculation gives a different shape, a line that only ever climbs and never comes back down. Two predictions about the same object, parting company at a specific moment in its life. And for a long time, nobody could derive Page's falling curve from gravity itself. It was what you got by assuming quantum mechanics wins, not something gravity produced on its own. Recently, that changed. Working independently, several groups returned to the calculation and included geometries that had been quietly left out of it, and gravity handed back Page's curve. The line climbs, turns over at the halfway point, and comes down. The mathematics has one deeply strange feature. Past that halfway point, a region inside the black hole has to be counted as part of the radiation outside it, not connected to it, counted as part of it. Under those rules, the information comes out. The Page is not gone. There is one more thing worth considering, and it is the reason nobody is celebrating. That calculation works in a universe shaped differently from ours, a simplified geometry chosen because the mathematics is tractable there. And it delivers an answer without delivering a mechanism. It says the information leaves. It does not say how the information leaves a real black hole, the kind sitting at the center of this galaxy. Nobody can point to the process and describe it, and it cannot be checked. The glow has never been detected, not once. No black hole in the observable universe has even begun to shrink. So this is where the field stands. Physics has arrived at an answer it cannot yet explain, about an event that will not happen for longer than this universe has so far existed, concerning objects nobody will ever get close to. It would be easy to call that useless. It is not. The rule being defended here is not a rule about black holes. It is the rule that says the past can be reconstructed from the present, anywhere, in principle, for anything. That rule sits underneath every prediction physics has ever made. A black hole was simply the first place we found where it might break. And if the answer holds, the consequence is harder to sit with than the paradox was. Because if everything that ever fell in is already out here, written into radiation that no instrument can read, then the boundary that defines a black hole was never the edge of a place. It was never a wall between an inside and an outside, which leaves the question nobody has answered, not whether the information comes out, how.